get started. First of all, just a disclaimer. I'm Yu Feng. I'm working on programming languages and software securities. I'm not a like authentic like cryptographer. So today I'm trying to do my best job to essentially present this paper about Zerocash, and it was originally from a whole bunch of great people from MIT, Tangians, and TLF, and so the original slide was the current slide was actually based on the original version from Iran Trauma to make sure that I do a good job in terms of deliver the core spirit of the paper. So let me start with the motivation. So, and the paper is trying to attach a province, a very general problem like in privacy. So it's originally like target for Bitcoin, but it's like private province almost like happens in exists for like a whole bunch of other concurrents as well. So we all know that Bitcoin is a decentralized digital concurrency. So which means that let's say if you are a person that holding certain amount of Bitcoin, so which means that in this case you can send your Bitcoin to your friends, but because of the digital concurrence, which is a little bit different from let's say physical concurrence like a US dollar or Chinese yuan. So in this case, you can potentially like double spending your coin and then send to someone else as well. So which means that in this way, so I think everybody know that one of the standard way to resolve this problem is essentially using blockchain in the sense that you try to broadcast every transactions into a public ledger, okay? And this public ledger is essentially an append-only list. They essentially contain a whole bunch of transactions. So in this case, essentially this solved the problem of double spending, but also it's essentially it bring a huge problems in terms of privacy. And here, what do I mean by privacy? For instance, there's many issues in terms of the privacy based on this architecture. For instance, so you don't, one aspect is about the consumer purchase. For instance, if you are Dahlia, so who just bought a house, and then you don't want to review how much the house is going to be, right? That's some kind of privacy. And the second issue is essentially, in example, is account balance in the sense that if you are someone that is like as rich as let's say Elon Musk or Ted, probably you don't want to like review your balance and stay low key and choose to stay low key. And there's many other instances, for instance, like as a merchandise, you also try to make your cash flow a little bit private because essentially, otherwise it's going to expose to your competitor. So, so you might wondering, so what's the issue? What's the real issue here, right? Because it's essentially, if you just look at the informations that publicly available on blockchain, even though they reveal some of the information about transaction like recipients and their sender, but most of them is essentially are kind of pseudonymous in the sense that like they are not actually real name like Hongbo or Hanzhi that you can infer. But even at that time, that was like around 9 years ago, with like the big data technologies, is essentially people can actually like uncover a whole bunch of private information by analyzing the transaction flows on blockchain. So I think today they can even do that in a much better job. And another problem is essentially a threat to the currency of fungibility, right? So it's essentially if essentially you can trace, if you can trace like the source of their, it's essentially the digital access, essentially like they might essentially run into some discriminate issues. And so, which means that originally it's essentially the whole point of blockchain is essentially we try to essentially mitigate the problems of a centralized bank in the sense that like in the original centralized bank, you only reveal your privacy to the bank. Okay. But here, when you move to a decentralized solutions like Bitcoin is essentially, it seems that the privacy problem is actually getting worse because right now, instead of revealing your information to the bank, you also reveal your information to everybody else. Okay. So that's essentially the key problem the paper trying to solve. It was published in Oakland 2014. But here, the paper is actually not the first one to solve it's essentially privacy problem. If you look at corresponding literature, for instance, one of the standard way for solving this like a privacy transaction problem is essentially you can think of it like there's a black box called a mixer. So what the mixer does, you can think of it's like a black box for doing like a laundry of your transactions. So how laundry transaction does is essentially, so there's a whole bunch of like transactions from the sender that go from the left hand side to the black box. And then so the black box is going to, the mixer is going to, it's essentially laundry those informations. And then when the outputs came out to the sender, so essentially you cannot tell like where the transaction is originally coming from. So which means it's essentially you remain like, as a sender, you remain like anonymous and keep your privacy with respect to the recipient, but you still is essentially like remain public with respect to the operator of the mixer. So that's why it's essentially in here, instead of like choose to trust a bank, it's essentially you choose to trust the operator on the mixers. So which means that theoretically, the mixer can is essentially potentially trace all of your transaction flow and steal your money if they want to. So as a result, it's essentially a prior work before the Zcash paper. There was a paper called Zerocoin, which is published from a subset of the same author at Oakland 2013. It's essentially their idea is essentially try to mitigate this kind of centralized mixer into a decentralized version. Okay, so which means that in some sense, essentially, it kind of mitigates this problem a little bit, and but also there's a lot of like still a lot of like uh, disadvantage that is essentially prevent is like a real adoption. For instance, one disadvantage is essentially limitation is the performance in the sense that it's essentially the performance essentially in terms of the time to validate a particular transaction almost close to 1 second. And then the second is the second issue is essentially the single denomination problem, in the sense that the coin that you're dealing with has to be like atomic, and then it's undivisible. So which means that it's essentially you can essentially map, let's say, 100 Bitcoin to your zero coin, or you cannot like map like a fraction of Bitcoin to your zero coin. And it also like it preserves some privacy, but it still like reveals some other information, such as like payment destinations. And there's also like this kind of explicitly like a black box that is essentially does the laundry process. And then simultaneously, there is also like some relevant works on the same years, which is called Pinochet coin from Ryan Pano. So it's essentially, you can think of it's essentially it uses ZK. It applies ZK to mitigate this problem a little bit, but still like there are some scalability problems, and then it's not fully like a privacy preserving, in a sense that you still can only deal with single denominator, and then you still like review the amount as well as the destinations, etc. And so which means that so the core problems based on the status of the prior work, so the core problems of this paper trying to address, essentially they want to come up with a fully preserve privacy, efficient, transparent, like system to is essentially mitigate all the above limitation. And that's essentially what this Zcash paper is about. It's a new privacy preserving protocol for digital concurrencies on top of Bitcoin. Even though the original paper was instantiated in the context of Bitcoin, but it's essentially you can basically like instant like a similar idea into like basically any other like a L1 chain like Ethereum, etc. And so some of the like a notable feature, which essentially correspond to the limitation that I mentioned before, in the sense that so here it has extremely flexible functionality, in the sense that you can send any zero coin to like anybody else as long as you have their public address. And it's also support variable denominations, in the sense that you can map a fraction of Bitcoin or 1,000, 100 Bitcoin to your zero coin. And then it's essentially nothing is going to reveal about your like origin, destination, and amount, etc. So which means that if you think about this is the original like a ledger on the Bitcoin mainnet, in which like everybody's transactions is going to be public to everybody else. It's essentially with the Zerocash protocol. So the entire information is going to be private. And so how does that happen? Okay, so let's first talk about the high level intuitions. So imagine, so you are the sender on the left hand side. Okay, you are the sender, and you know that you have some money in terms of cryptocurrencies from somebody else last night, and then you haven't spent any of them. So which means that in this case, you are for sure that you can essentially pay a certain amount of money to a certain merchandise on the right hand side. Let's say you want to buy some grocery, you want to buy a car, a house, etc. So which means that if you want to do that, and then so one of the naive way that you can prove to your like merchandise on the right hand side is essentially you just show, hey, this is my current balance, right? I want to prove that I indeed I'm sufficient enough to is essentially pay this 70 Bitcoin. But you don't want to do that because if you do, the moment you do that, it's essentially you reveal all your privacy. Okay. So what can you do in this case? So the way you can do is essentially, well, because I don't want to I know some fact, right? I know that I have sufficient enough balance to cover this 17 Bitcoin. I know that this fact, but I want to convince the merchandise on the right-hand side that I what the statement is actually true without actually revealing any information about the statement. So what you can do in reality, right? Um, you can is essentially you don't want to reveal those information to the merchandise, but you can essentially reveal those information to accountants on the left hand side. Let's say this accountant is very senior accountant. Everybody trusts them, right? So it's essentially so these accountants. What you can do is essentially you can provide those facts to the accountants um, on the left hand side, and then so these accountants once this accountant convinced that the information is true, they're going to he's going to put the signature. He's going to put the signature on a piece of paper and then show it to the merchandise in the sense that, hey, I can definitely prove that with my essential reputation that this essential sender have enough information. Okay, so that's essentially the real world protocol to essentially resolve this privacy problems. So you can think of with zero knowledge proof, it's essentially you can think of what you really want to construct is essentially is like a virtual like accountant because the original like model, even though it solved this problem, it has multiple aspects. The first aspect is like it's interactive, right? It's essentially every time you want to make a transaction, you want to make sure that the accountant is nearby to essentially vouch for you. You don't want to do that. You want it to be completely fully non-interactive. And it's essentially what they, and you also want to make sure that this virtual accountant is essentially does the job that you want, which essentially you want to prove like some statement without reviewing those kind of statement. And that's essentially the job of zero knowledge proof. And that's also the foundations of this paper. And so it's essentially, before we jump into the details, like let's take a look at some like end-to-end performance matrix. It's actually pretty efficient in the sense that it can essentially generate like 280 per byte per every transactions at the level, the secure level of 128 bit. And then it's very fast to verify. For instance, if you remember the prior work, which take almost a second to verify a proof, with Zcash, it only take like a few milliseconds. And so the proof generation is moderate. It takes less than a minute to create. And so, and the initial like trust data require around 1 GB the storage to support, which is essentially like moderate and can be afforded by majority of the essentially systems and machines. And so essentially once it's essentially they have this kind of initial trusted setup, and those initial setup just need to be run once. And then it also is essentially based on a couple of crypto assumptions in the sense that like it's based on elliptic curve crypto, and it's also is essentially based on like whatever the property support by SHA-256 and etc. So with that, essentially, let's jump into the actual design of the system, the Zcash scheme. Okay? So before we actually jump into the full-fledged version of the Zcash, let's first start with vanilla versions. And here in the vanilla version, is essentially, let's say we don't support like variable denominations. Okay, so it's essentially one Bitcoin is always going to convert into one, let's say, zero coin in this context. So in here, we want to, it's essentially design this kind of privacy preserving protocol without it's essentially review any of the sensitive information like sender, recipient, amount. And in particular, it's essentially we have to deal with two core functionality. One is the mint function, which is essentially producing those coins. And then the second is the spending functions. Okay. So, and then it's using those two functions, you can essentially compose with many complex other functionality as well. So in here, what you can do is essentially, you can, based on the prior work from Sender to Sharma. So it's essentially, you can come up with a polynomial commit schemes in the sense that, so instead of directly reviewing your series number, so here you can think of the series number is a unique number that corresponds to the digital concurrency. Okay, so just like if you use a US cash, like $100, there's always a unique series number. So in here, you don't want to directly review this number. So what you can do is essentially you can come up with commitment scheme that is going to take two inputs, and one is the series number, okay, and the another is the random the commitment randomness R, and then it's going to generate an output called like commitment that corresponds to the coin. And this commitment is essentially is going to have two properties. One is essentially if you essentially know the series number as well as the randomness, it's essentially you can quickly verify. And also by just observing the original output, this commitment, so you cannot infer any information regarding the series number. So let's see how it works, right? Let's say, suppose right now I want to implement this mint functions. And so, and for minting a particular coin, let's say zero coin in this context, I have to spend like 1 BTC first. And so, which means that the series number at the bottom is going to correspond to the 1 BTC series number. Okay. And then with this information, is essentially you can mint as many zero coin as many as you want, and the public ledger is going to essentially maintain a list of this kind of commit number that correspond to the available like zero coin that people can spend. Okay, so this looks good because essentially based on this commit informations, you cannot essentially infer like the actual number that's it's essentially that was originally minted. So what about spending, right? So in here, let's say someone else came up and he wants to spend a certain like a zero coin that correspond to a particular series number. And essentially, in order to spend that, it's essentially this guy is going to provide both the series number as well as the CM and the randomness. Okay, so in this case, essentially, you can think of it's essentially even though like the original information get preserved, but once during spending these transactions, you still have to essentially review this number because the series number based on the series number as well as the R, the randomness. It's essentially the public user can essentially trace back to the user who actually do the original minting. So which means that you lose privacy in this sense, and you don't want to do that. So what the paper does is essentially with zero knowledge, what you can do is essentially instead of like maintain a list, you construct a Merkle tree. Okay. And you construct a Merkle tree in which like you roll the Merkle root, and here instead of directing reveal the fact that you try to consume a coin with a particular series number, which is essentially going to reveal the information. And so you essentially turn into a statement in the sense that, hey, I know some randomness number R as well as commitment CM in a Merkle tree of a particular root number, okay? And then I make sure that those information is going to map to a certain series number that I'm trying to spend, but I'm not going to tell you which series number in the Merkle tree. It exists, okay? It exists in the Merkle tree, but I'm not going to tell you which one. And then, so I'm going to show you a zero-knowledge proof to prove that whatever I say is going to be true, okay? So this is essentially vanilla version to is essentially show you under it's essentially simplified setup. Simplify in a sense that if you don't support a variable denomination, how can you essentially use a polynomial commitment scheme to essentially as well as to essentially derive a private preserving protocol. And so in here, it's essentially, as you can see, in the sense that the spender, in order to make a transaction, is essentially he can essentially claim some a statement without actually reviewing what those statement is going to be. So which means that in this case, it doesn't need to be interactive, right? You don't need a virtual, you don't need a physical accountant, okay? And then it's also zero knowledge in the sense that it's essentially the verifier can essentially validate this statement without inferring any information about R and the series number. Okay, and it's also extremely efficient, and that's essentially the zk-SNAP protocol. And in practical, so it's essentially depending on the setup, it's essentially you can run the zk-SNAP protocol with a trust setup and without a trust setup. It's essentially just both pro and cons. And I'm not going to dive into the details. And so here, the setup, the choice of the current paper is essentially use a trusted based setup, which is essentially based on the lib snark built by the same co-author as well. So now we support with zk-SNAP, you can actually encode much more powerful functionality in the sense that you can almost essentially encapsulates any Turing complete computations. And let's see how we can expand the original schema to support more powerful functionality. Okay, for instance, previously our schema is very simple in the sense of we assuming that we don't support variable denominations, and every Bitcoin has to is essentially uniquely a map to one particular zero coin during the mint process. And so what about we want to mitigate that problem, right? We want to add support about variable denominations. So in here, it's essentially, let's say, I want to map in order to mint a particular zero coin. So I want to map to a corresponding V amount of Bitcoins to do that. So this V can be an integer. It can also be a real number that corresponds, let's say, a fractions of the data. So in here, what you need to do is essentially you can essentially slightly extend the original architecture by adding additional layers in the sense that you have one original layer that is going to deal with the value that correspond to the mapping that you want to add. And then you also you also have the second layer that try to encapsulate the informations of the series number, which essentially the information that you want to hide. Okay. So in here, it's essentially the same thing. It's essentially given this kind of a new a schema. So how are we going to design our new interface? And it's going to be very similar. For instance, during the minting process, let's say, in order to mint a certain one, zero cash coin, right? So in this case, I want to generate a commitment CM at the top. In order to do that, it's essentially I have to spend V amount of Bitcoin. Okay, I have to spend V amount of Bitcoin, and then it's essentially, and so here is essentially by extending this schema, I also need to provide additional parameters such as K, R prime, etc. So this is essentially the minting procedure. And during the spending procedure is similar. It's essentially, for instance, what you really want to do is essentially is a statement in black in the sense that I want to use up a coin with, let's say, a particular value V that corresponds to a certain series number. Okay, but I don't want to reveal this information, even though this is what I really want to do when I do the spending. But I don't want to reveal this information. Instead, what you provide is essentially generate a ZK proof that is essentially state the statement at the bottom in the sense that I know some parameter R prime and R double prime that are consistent with the commitment. Okay, you can see the, like, everybody can see the number of the commitments, and everybody can also, like, I can also share this R prime and R double prime, and essentially those information together with the zero knowledge proof that we generate is sufficient enough to convince the, let's say, the merchandise or my friend that essentially I'm going to is essentially spend this amount of money that corresponds to the series number. And with the same philosophies, essentially, you can make this protocol even more like sophisticated and more interesting in the sense that right now, let's say I want to directly like adding anonymous payments, right? Anonymous payment in the sense that it's essentially in this case, in order to do that, I need to provide this address, right? This address. So this address can correspond to like two parts. One is the public address, APK, that everybody know about that. And then the second one is essentially the secret key. And the secret key is essentially something that you don't want to share. So in this case, as you can see, it's essentially the philosophy of supporting like a direct, like anonymous payment is going to be similar to what we did before. Is essentially all we need to do is essentially add by adding one extra layer on top of like what we already have. For instance, originally we start from a vanilla version, we extend to support variable denominator, and then we keep going and add one extra layer to essentially like support like this kind of a direct anonymous payment. And here by dynamic, so in order to hide the information such as like a secret address, so as well as a series number, so the author is leveraging pseudo random functions to essentially generate like from the outsider, it look like a random series number, but with the private key as well as the actual like series number, you can essentially deterministic like generate this kind of number. Okay, basically from the outsider, there's no like actual information you can infer from those from those numbers.
I have a question.
Mhm.
So what's the range of R in this protocol? Let's say the random number could be extremely large or
I think it's 128 bit. 128 bit. I need to double check offline.
got it, got it. And I have another question that we have many inputs for the protocol. Let's say the secret key must be a secret, but for the serial number and the randomness number show them be secrets for the user for
So
the
the series number has to be the series number has to be secret. The series number has to be, this row, this series randomness series number can be public. Like basically, like everybody can see this like a random series number, but it's essentially based on this random series number because it's generated using a pseudo random function. You cannot infer any information about the secret key as well as the original series number. Okay.
got it, got it.
Okay.
Um,
So any other questions?
I'm sorry.
Yeah, so I don't know if this is a good place to it's not so much a question, but kind of a discussion. I don't know if it's a good place to stop or if you want to continue a little bit and then I'll discuss. So,
No, you can stop me anytime. It's like a
all
discussion.
right. So a couple of things. I'm obviously familiar with the Zerocash for a while. So first of all, at a high level, a big discussion, a big comparison point between this and mixing techniques is that this is a hard fork. This is not compatible. This is not just mixing payments before you submit them to Bitcoin. You cannot submit this to Bitcoin. There's no way to verify
No, right.
these
it's
transfers
half
on
fork.
Bitcoin.
Yeah, it's a half fork.
So the way Zerocash or Zcash launched was anybody that wanted up to a particular point had to transfer their coins to an address. That created this pool of private coins, and from there on it forked. It doesn't continue on the original chain.
Yeah.
I actually wonder, as a discussion point, now that we're starting to have layer 2 solutions, whether it may be interesting to to do all of this on a layer 2 and then a checkpoint on Bitcoin every once in a while, and maybe that would be possible now. So a layer 2 could now enable this, I think, on the original Bitcoin or something like that.
Yeah, that's essentially what Aztec is that like I think it's essentially what Aztec is doing, right? For instance, I'm not sure whether we have a colleague called Schumer. I think he was in US at UCSB and then he left for doing the mentor network. And essentially what they are originally doing is essentially it's Mentor is building a layer 1. Mentor is building a layer 1, and then it's essentially what they are doing is essentially is doing this kind of privacy preserving like a blockchain. Um, so, okay, I see what you're saying is essentially, so you want to do that in the layer 2, you want to do that in the layer 2, and then you settle on layer 1. So Hunter, do you know any like layer 2 solution on the aspect? Because I think Aztec is also a layer 1, right?
Yeah. Ethereum layer 2. So and private preserving layer 2. So yeah, say already like settled on Ethereum and keep all the like states and balances private for their users.
Oh, I wonder if we could
And
do it with Babylon now or something like that as another use case of Babylon or something.
yeah, I think we can do it now on Bitcoin. Like similar to the Aztecs technique, but we first to like implement some kind of CK verifier on Bitcoin, and based on the previous techniques we had discussed.
All right, something to think about. The second comment, sorry, Shuyan, you wanted to say something?
Sorry, my network condition is very bad. It's lose connection from time to time. I thought of a solution called Tumblebeat. I can't remember all the details, but I don't know maybe what was it a layer 2 solution or not.
Oh, sorry, what's the name?
Tumblebeat.
Okay.
Okay. Yeah, maybe as a research question, maybe it's worth looking at. I'll look at Tumblebeat. The second comment I had, again, high level, is there's still a point which is probably the most vulnerable in terms of privacy. I, as a user, with all this zero knowledge technology, with everything, I have to connect to some operator through my network connection. And that operator knows that I am transacting. They may not know exactly what I'm doing. They may not know how, the value of my coins. But if they see a transaction, or a block later, they know that I am transacting it.
Yeah.
There's always that point, right?
Yeah. So that's essentially like that's essentially the same issue with Tornado Cash, right? In the sense that, for instance, if I want to, let's say, laundering my money, it's essentially, let's say, like for good like I say, it's essentially like when I, let's say, like making a deposit to let's say Tornado Cash. So it's essentially I cannot directly withdraw, or I cannot directly use that, because essentially if I directly use that or spend it, it's essentially I will immediately run into the issue that you mentioned. It's not just visible to the operator, it's also like visible to like other. It's essentially like they can infer those kind of information like based on the pattern. So what people typically do is essentially you have to wait for a certain amount of time to make sure that there is enough. Basically what they do is essentially still like doing this kind of mixer. So essentially you have to wait a certain amount of time depending on how active your network is going to be. Could be a few hours, could be a few days or a few months. So that's why I was like wondering whether there's any like a further advanced technique that can bypass this limitations as well.
I mean, there are, okay, so first of all, even if you wait, the operator themselves, they know. So yeah, you could obviously go through some anonymizing network. You can send, you can connect with the operator through Thor, or other makes it. But yeah, it gets more and more complicated to do that.
Yeah.
And in
and
fact,
even if
when the government agencies, when they raided on tornado operators, this is what they raided. They raided the people who allowed bad actors to launder their money through them and connect. Oops,
Yeah, yeah.
losing my headset.
Maybe
yeah, and
Monero
and even
makes money faster a little bit because it's obligatory in Monero to mix in sufficient addresses, and it grows exponentially. For Zerocash, it may mix out a little bit slower.
And as for these like off-chain identity informations, we can even identify certain people by analyzing the like IP and timing data, like who sends like IP package to those address. And yeah.
Okay. So shall we move on?
Yeah.
So okay, have muted. So yeah, basically, I think here is essentially, this is actually addressing Hongbo's early question in the sense that, for instance, in this case, what I really want to do is essentially I want to use up a coin with that correspond to a value V of a particular series number. But what I'm trying to do is essentially I'm trying to like show zero knowledge statement to prove that I know some like R prime, a double prime row, as well a public key that corresponds to the address I'm going to send. That is essentially going to consistent with the commitment. And then, but I'm not going to reveal like what those detail is going to be. And so it's essentially, so if you want to send like let's say if you want to send a certain amount of money to your friends, and so it's essentially you can almost reuse the same scheme that we showed in the previous slide in the sense that in here it's essentially all you need to do is essentially you're going to construct a tuple that contain, let's say, 4 elements that correspond to the value V that correspond to and this value V, and also the 2 parameter R prime and other double prime, and then the last one is essentially this series number randomness that correspond to the original series number as well as the private address that you want to hide, and then it's essentially it's the same guarantee in the sense that the recipient is not going to essentially reveal or infer any information about those that you're trying to hide. So I'm not going to go to the details. And then finally, it's essentially there is what they want to do is essentially they want to come up with one general transaction type that is going to handle everything, because you don't want to is essentially design one schema for every single like scenario. For instance, I want to send a payment to my friends, and then I'm going to consume a certain amount of zero coin by making change to my balance, and I also want to do swapping, right? I want to like exchange my current zero coin to Bitcoin, and then finally, it's essentially I also want to pay the transaction fee of the miners. All this kind of stuff they want to unify with a single like a transaction type scheme, and which is what they call this pool function. And what this pool function does is essentially you can think of is take input from this old like Zerocash coin, and then it can essentially generate like a new like a balance of the new like Zerocash coin as well as some public Bitcoin, depending on what kind of transaction that you want to do. And then you can essentially make your like transaction and business logic even more complex. For instance, you want to specify how are you going to want to split the money, and then what are your destinations, and then you can also selectively choose to like the amount of value that you want to is essentially expose, and then all this information will guarantee to is essentially like revealed to the public properly. And then finally, it's essentially the additional information you want to output is essentially the series number SN1 and SN2. And then the reason that we want to reveal those series number is essentially you want to avoid double spending. For instance, if someone like already spent, let's say 10 Bitcoin on his balance, it's essentially those information need to pull out. So that's essentially like he or she cannot like do the double spending anymore. And then also it's essentially all these kind of commitments that we already went over. And then it's essentially finally what you want to do is essentially you want to have this kind of virtual account, which essentially a zero-knowledge proof to is essentially certify the validity in the sense that the sum of the old coins is going to guarantee to be equal to, let's say, V1 plus V2 plus is essentially the remaining number of the Bitcoin that is observed by like everybody. And then, so this is essentially the white box from the designer's perspective, from the prover's perspective, but it's essentially what it is going to show up. It's going to be the information at the bottom. For instance, what the public can see is essentially it's essentially serious number, because it's essentially if it need to be used to prevent like a double spending, as well as those commitment. And from the commitment is essentially there's no way you can infer like additional information about the senders and amount, etc. And finally, it's essentially the zero-knowledge proof. And this is essentially the visualize of this design, and this is also what you will show. What you can see is essentially from the ledger of the Zerocash. So it's essentially, for instance, you can see the number correspond to the Merkle rule. You can see those two series number, and you can see the commitment number. And then essentially at the end, is essentially one thing I want to mention is essentially is this zero-knowledge proof. And this zero-knowledge proof is essentially is to be used to let's say allow hundreds of thousands of people to validate it's essentially validity of this transaction. And notice that it's essentially the size of the proof is pretty moderate. It's around 1 kilobyte, which essentially can be done by like any like a normal machine. And then essentially I'm going to wrap up the rest quickly. It's essentially at the end, essentially all those designs that I mentioned in the past it's essentially being implemented into a decentralized anonymous payment system, or DAP. And then it contains a couple of core algorithms. It contains the initial trust setup, okay, and it has a setup function. It has a create address function. It has the mint function that I mentioned. It also has a pool functions that I just introduced in the previous 2 slides. And then it also has a verify transaction function that allows the user to essentially effectively like take those information from the public ledger as well as the proof, and then verify the validity of the transaction. I'm not going to go into the details. And there's a whole bunch of words in the paper that need to prove the security of this system. For instance, some of the notable security, including ledger indistinguishable, in the sense that it's essentially they prove that it's essentially with the like Zerocash system, there's nothing actual informations are revealed beside like the original public information available for is essential from the Bitcoin blockchain. And it's essentially, and the proof is actually not specific tied to Bitcoin blockchain. You can essentially generalize into other like L1 blockchain as well. And then the second is essentially the balance. It's essentially also prove that it's essentially like there's no double spending will happens. And the last one is called transaction non-malleabilities. So what they do is essentially they want to show that essentially because there's a window. What do I mean by this window? Is essentially starting from the time in which you initialize the transaction. Let's say I want to send 10 Bitcoin to Dahlias. And then until this transaction actually gets settled on the Bitcoin, there is a time frame. And then you want to make sure that during this time frame, nobody else can manipulate or alter the transactions during the past. And they also prove that. So in the end, it's essentially everything. The entire system was being implemented in a very sophisticated system that include like the zk-SNARK library they built by the author, and then also include the library corresponding to Zerocash. And then at the end, they actually like instantiate a fork of, I think this is probably relevant to Dahlia's early question. It's essentially, instantiate on a fork of Bitcoin network on EC2. And then it's essentially, the performance is on the right-hand side. So I'm not going to essentially read it aloud. It's essentially, I think the takeaway is essentially, they try to simulate a whole bunch of real transactions from Bitcoin. Essentially, it turned out that it didn't like significantly impact the user experience and then there's no traffic jam, and then there's no like a huge delay. For instance, I think the verification time is pretty fast. It take about like a few amount of like a millisecond to validate the validity. And they also, as I mentioned earlier, it's essentially in order to set up the system, it's essentially they are doing that. They require a trust setup, and the setup is actually a fair amount of work. But the nice thing is essentially you only need to do that once, and it's essentially to generate all the relevant key for both the parties, including the prover and the verifier. And then it's essentially, and then the guarantee is essentially, even though like the setup can be potentially compromised, but you still preserve your anonymity. So, and here the question is essentially, is this possible? Is essentially to eliminate this setup. So, which essentially corresponds to some of the open questions proposed by the author, and it's actually pretty like amazing that you can see that they propose these questions, but actually a lot of questions are actually being actively addressed by a lot of like industry and researchers in this space. For instance, they mention a lot of interesting problem in the sense that how do you essentially specify a very complex like a policy, right? For instance, because one of the biggest like a blocker of applying this kind of privacy preserving blockchain is essentially, in a lot of cases, it's not just about the technique. It's actually like about like there was a lot of legal and compliant issues. So which means that if people really want to push the boundary of this space, it's essentially like we also need to support like a very complex like policy that is essentially could potentially like a leverage, at least essentially make sure that the network was not just being used by a lot of like bad guys and for essentially illegal purpose. And then the other applications that mentioned by the author essentially correspond to like a blockchain compression, right? This blockchain compression is essentially the idea of like most of the L2 nowadays is essentially you can actually essentially use like zero knowledge proof to essentially like a package a whole bunch of transactions together and then just like store the proof on the mainnet. And then you can even like simulate like a tooling complete programming languages, which essentially what everybody is doing right now. And then this proof of reserve is actually a big topic. I think after the crash of like FTX, and then people also try to essentially like apply zero knowledge proof to essentially do this kind of proof of preserve problems. And yeah, I think that's pretty much the main things I want to present today. And then we probably have a few minutes for discussion.
I have another question. So for the essentially for the the snack, it should be stored on the public ledger, and for both it's the same for the serial numbers and the CMs, right?
Yeah. This is
And so
Yes.
does the author say where should be the public ledger? I mean,
So what do you mean?
could we store the public ledger on our DA? Because let's say the storage on layer 1 is so expensive.
But if you store the DA, is essentially your DA, the DA is not going to be persistent, right? You can, but it's essentially depending on like whether you want to make those data persistent or not, right? If you want those information to be persistent, that it can be validated by anybody anytime. So then it's essentially you need some kind of a IPFS, like this decentralized versions of like a storage system to do that, right? Because
Yeah.
otherwise, essentially, if you use DAs, essentially the information is going to be gone like after a certain amount of time.
But we could renew the lifetime of the public ledger.
Yeah, of course.
Okay. That's all my question.
Any other questions from the audience before we wrap up?
No. I think Zerocash is a very solid design, and I didn't understand all the details because partially because of the network condition. And just one question. how the pro transaction avoid the double spending if the adversary node does not have sufficient funds?
So the series
Sorry, I
number,
missed some information because of the network issue.
so what's your question? Because the
Oh,
series number is going to be output, right? Can be validated. Like this series number is not, it's not secret. It will be essentially share to the public. You just cannot infer where those secrets number is coming from. So which means everybody
I see.
know like the series, a certain amount of 10 Bitcoin already spent. So which means that it cannot be used anymore. But you just don't know where this series number is coming from. It can come from Dahlia or come from Hanzhi. You don't know about that. But you do know that this
Yes.
already gone. So no matter like how bad or like your network issue is going to be, as long as it gets settled on the
I see.
ledger.
So the series number will be released after one payment.
Yeah, that's my understanding.
Thank you. That's all my question.
Any other questions from anybody else?
I guess not. Thank you, you. This was a very insightful, enlightening presentation, including the historical context and overview at the beginning.
Thank you, thank you, thank you.
Thank you so much for the presentation. I learned a lot about the history and the implementation of the and the design principle of the Zerocash. Thank you.
Okay, thank you. Then I will see you all next week.